This is video number 24 on June 29th. It's going to be about how and why electric current flows, part B. It's time we quit thinking that the average person can't understand these kinds of things. The reason this is a widespread impression that that the average people can't understand these kinds of things in physics, because I'll tell you why that is. Okay, it's because it's used as a status symbol. It was falsified. It was made artificial, like a religion does, and because they couldn't crack the real naturalistic explanation, so they came up with some artificial ones, and of course built on those. I'm not saying that everything is wrong. It's funny when you look into these things that, you know, when it comes to relativity, they praise relativity. When it comes to actually using relativity, they don't use relativity. It's always more like Newtonian physics. Whenever they do anything, it's always just like kinetic, simple, just like things you would observe in the natural world every day. You know, pretty much just applied in physics. And then we give this homage to relativity, like we couldn't do anything without relativity, and that becomes the icon of physics, relativity. Well, but the reason average person can't understand these things is because too much of it doesn't resemble the natural world they live in and observe every day. That's why. All of it needs to be made so it resembles the natural world that we live in every day. Then it's not going to be exclusive to some people who use it as a status symbol anymore. It's going to be available to anyone to understand and embrace. There is something special about special conductors like copper. I would say aluminum's in the same category. It's not as good. There are other special conductors like, for instance, silver and gold. This is similar to noble gases. In noble gases, you have helium, and there are several elements. Then you have neon, several more elements. Then you have argon, several more elements. Then you have, xenon, several more elements. You have krypton. These are noble gases. They generally don't attach to they don't make diatomic molecules. They don't attach in compounds. There's something special about noble gases, and it repeats in the periodic table. It's all good information, but we don't know why. That's the kind of thing we need to find out. See, that's being ignored right now. It's like, oh, as long as we can make money and do things, then who cares, you know? Once you crack these kinds of things, religion is going to go away. Don't you understand that? This is the philosophy of science. This is the philosophical side of science. When you understand the why, then the whys that have implications about whether people adopt religious faiths or not go away. So we want to know why we want to know the mystery. We want to solve the mystery. Instead of just making an application all the time that people can use, which is great. That we need those first. We don't need to understand everything to do things that we can use that helps the world, like in medical science and all these. That's great. But we also need to solve what's going on in the human mind, the problems, a lot of those problems that are going on through physics, by understanding what our existence is really like. Anyway, what is causing noble gases? Okay, why are some conductors special? We want to know why. We should find out why, okay? Anyway, when it comes to copper, I think there are a couple of options how to explain electric current. And I will tell you right now, it's not what the standard model says with regard to electrons. Okay? Somebody made that up and it's artificial. Sorry. There's an electric layer, it would appear, next to the nucleus. Now that is below and next to the nucleus, closer to the nucleus than any of the spherical filled radio shells that progressively envelop the nucleus moving out and cause this gray dot around the nucleus that you see when you look at atoms, lensing, and cotton fabric when viewing them through direct sunlight. Okay, those are the radio shells. Out from there are the larger unfilled electron shells and these larger atoms that have those. I've already talked about this. It is possible that in these radio shells that when you are disturbing, and I said this wrong once in a while, I use the wrong word, like say proton for neutron, so you have to overlook that. It doesn't happen very often, or I'd have to redo the entire video, so I allow it usually in one or every other video or so. I say the wrong word and then I have to leave it because I don't want to redo the entire video. I redo it enough as it is. Anyway, one of the misstatements I made yesterday in a video was that, and this comes from the first book, before I understood that or had seen that radio shells envelop nuclei. What you have is what I said was that when you turn the rotor in a dynamo, that nuclei surfaces are disturbed. Okay, that would be true if you had planar electron shells and there weren't any radio shells surrounding nuclei. That would probably be how it works, but that's not how it works because the nucleus is to some degree protected by those radio shells. Now there's stuff that can reach the nucleus, I think in magnets, that the scouring of radiation, that it does create deficits on the nuclei, on the nucleon surfaces of the nuclei. I don't think those are deficits on the radio shells being restored. Could be, but anyway. But one of the things I said yesterday that's I've had to change is that it's the radio shells that are being disturbed when you turn a rotor in a dynamo to generate electricity. And so this allows for the more fleet electric photons to come in and occupy those places in those shells. Okay, that's what you have going on with the dynamo. Now down the line, you don't have this with copper. You're not disturbed in the copper wire that carries this electricity out from the power plant. You don't have this disturbing of the radio shells. But for some reason, when you have this buildup in the rotor, it's shared into the copper wire because there's a propensity in copper to take on a greater electric loading. So why is that? Let me back up and make a correction before I proceed any farther with this, so I don't have to change the video. As far as that scouring I mentioned with magnets, it can't be the radio particles. We've already talked about recoil and how visible light interacts. I don't think there's any chance that could be the radio particles that they're spongy. They can move, they can vibrate, they can, whenever something moves when it's being struck. Now when it recoils back and there's a collision, now you have a powerful collision, more powerful than if it was standing still. But But when it's since it's in effect sort of spongy in that situation where there is repel holding it in position, um, then you're not going to have those units losing photons. I don't believe it's with magnets. It still has to be the surfaces of nuclei that are losing a few of their photons that help it to um, to be neutralized enough with the environment. So we have a couple of options, I think, with what's causing something like copper to be such a good conductor, better than, say, carbon and many other elements. You talk about sulfur or sodium. I really haven't looked into sodium as a conductor or what that would involve. A lot of elements out there that could be used as conductors. They're going to have different amounts of resistance, but we do know this as far as where I stand with my knowledge of conductors at this point. We know that copper is a better conductor than a lot of elements. And so we're going to talk about copper mainly. With what makes it so special then? Now, what you're going to have with these radio shells is they're going to be filled. Okay, I've already mentioned this, but my camera phone wasn't recording. I'll go over it again. When you're assigning 88 electric particles per protons contained in a nucleus, and you have that figured out how many, according to how it would configure with that number. And then for every neutron in a nucleus, you assign 110 radio particles. Okay, you take your first shell, which you figure the diameter of the nucleus. I've already said this, but I have to say it all again because it wasn't recording when I said this. You have the diameter of the nucleus, then you figure that, and you can figure a volume. Then you have the electric photon layer out from that because they're more fleet and they're going to take up positions next to the nucleus. They can't land because of what I just said. There's too much repel. Once a lot of those little photons that repel attach, now you have too much repel and they have to hover. So they're hovering around it. Not over neutrons so much because neutrons have more surface repel, but over the protons especially. Now you have the first radio shell, and depending on its unit, you would plot them on a spherical shell around the nucleus, and it would you figure that by the area of a sphere at that distance. You can mathematically determine exactly if you have your values right as far as repel, your distances, spacing correct, then it would be there would be a specific distance out from the nucleus, and you would plot those according to the repel to one another, and it would make a spherical shell. It would be completely filled. Now, when you do that, and you've got a certain radio particle, you can determine what the capacity is. Now, you look at my table, you see that there's a capacity for each shell at that area of a sphere for each individual kind of radio particle, whether it's an R15 or R3 or an R6 or an R5 or an R4. All of those would have a certain capacity at that area of a sphere given the nucleus size and then where this shell would, the distance this shell would occupy, which is different for every element depending on how large the nucleus is. Anyway, So when you do this, you come up with a certain number according to the number of protons and neutrons. 88 per neutron, 110 per, or 88 per proton, 110 per neutron. And so you come up with a number, usually in the hundreds, often the hundreds, sometimes over 1,000. But so according to the capacity of that shell at that distance, at that size, at that area of a sphere, now you put in whatever the number is for that first shell. Then whatever's left over, you put in the next shell. And then pretty soon, okay, you get to a point where all these shells are filled, but you have an unfilled shell with the number that the nucleus requires for it to be essentially neutralized with the environment and not keep attracting things in to hover. You're going to have a certain number in the outer shell. I think this is what's going on with special conductors like copper. I think that there is maybe there could be 3 of those out there that are orbiting. The reason they orbit is because they're not filled shells and that they're being exposed to incoming radiation. In a particle system where everything has mass, everything is kinetic. It's either repel, attraction, or kinetic. When I first started presenting this idea, I call it kinesis, which means something else, but you could start using it for this as well, perhaps. But you have a kinetic relationships all the time where things are colliding. And so when you have orbiting, let's say if you have a couple of dozen left over and it makes up this next radial shell, they can't cover it. You could have a half-filled radial shell out there. You could have a 25% filled radial shell. You could have a 10% filled radial shell. Let's say it's 10% or it's 5%. And so they're orbiting. They're orbiting because they're being struck by incoming radiation particles. That's what you have when things have mass. Everything has to have mass. You're going to have collisions. And those collisions are going to push those hovering particles in a certain direction. Once they're started in a certain direction, they're going to have momentum, just like the macro world where we observe momentum in our cars every day. Momentum, we put the brake on, we feel the desire to keep going. When you slow down, you feel G-force. So there's your momentum. Well, these particles have mass, and they have momentum too, and that's why they're orbiting. They're not magically orbiting like the standard models suggest. That's not what happens. These things are microcosms of the macro world we observe every day. If you knew what was really going on, you could comprehend it because you're watching examples of it every day in what you're observing and interacting with on a daily basis in the natural world. But they don't have to be continually hit to orbit. Now, if they're not hit enough to orbit, they're going to lose velocity and slow down. That's what you have cooling. But they're going to have a certain momentum and they're going to keep orbiting. And then, and that's what's going on. As far as electric current, you've got being taken on by copper wire, let's say. You're not disturbing the radio shells. There's no rotor being turned on down the line with electric wire. Now you have there is some circulation, of course, with the flux lines, but that's a result or a product of electric current flowing through the wire. That's not a cause like it is with the rotor turning. You have to have the rotor turning in the dynamo, disturbing so that something else can take its place, which would be the electric photons, taking the place of radio particles. Anyway, the two options I'm seeing for this, why copper is such a good conductor, and why is copper wire, when it touches, the what the materials leading back to the rotor and the dynamo, uh, its natural desire to take on more electric flow and then share it on down the line. I think it could be that the spacing between the radio particles and the radio shells, that could be an area where you have a perfusion being produced at the dynamo, at the rotor in the dynamo, that perfusion changes the environment of the proportions of electric photon available at close range, and they jump into and in between the radio shells. That's and maybe fill it if there's enough of that going on. Maybe fill those areas in between, not so they're all lost. Maybe some of them are lost, the radio particles, but maybe could possibly fill it all the way down to the electric layer. That's one option. Another option to explain that. Another option is these orbiting. Let's say you have a 5% filled shell in copper, and it's orbiting on its outermost radio shell. And now you're talking about what causes orbiting. It's being struck. Now there's a certain amount of momentum, so they don't have to be struck continually. Now they can be struck so they slow down if they're hitting the opposite direction, but I won't go into all that. But anyway, they're orbiting. And once they get a direction, an orbital direction, there's a tendency to maintain that direction. And that's a whole other study right there. But the basics of it is particles colliding into those are causing the orbiting. And when you have collisions causing the orbiting, not necessarily continual, but from moment to moment, there's a collision that helps it to continue to orbit in that direction. Now, it doesn't need that to keep going because we've already talked about momentum. Momentum means once it establishes a direction, whether it's straight line or circular, it wants to maintain it, keep going and keep going. Unless, you remove that for a long time, then it begins to slow down. Okay, now, when those are struck, they're not moved straight ahead every time. They're moved to the side. And that could be where the perfusion of electric photons in the rotor, that could be why they're shared in copper. That makes that outer shell that may be 5% filled may become vulnerable because of strikes that knock those radio particles in that shell over a little bit. And so this makes the possibility of those being supplanted by electric photons occur. And then it can escalate as there are more strikes that perhaps knock the electric or the radio particles in that shell to the side somewhat. And so that gives an opportunity for electric photons to supplant them in that orbiting. And now when you have a perfusion of those electric photons in that outer shell, now you've changed the environment of what's presented to the next copper atom on down the line. And so and then they jump from that one to the next one to the next, and then they keep jumping from the source at the rotor, and they're shared. And once you stop the rotor, then it turns it off, and everything goes back to the proportions they would have with radio particles, which would be preferred at that level out over a nucleus. And so I think that might be the explanation for that. I want to mention one more thing here about assigned values that we use every day. When something is determined before it's really understood, like let's say a Coulomb. Charles Augustin de Coulomb decided on a value for electrons. This is before anyone knew what an electron was, if all the electrons were the same or not. They assumed that all the electrons were. Anyway, they came up with a value of a certain number of electrons uh, is a charge comparable to, say, that of a proton or a positron. Um, you come up with a large number. Whenever you calibrate something, it doesn't necessarily mean you have that number right, but you calibrate from that point. And so you take magnitude, whether it's below or above that, and then you can say, okay, assign that. And then you have a system with something that is calibrated, a value that you can use. And you continue to use that, apply it, and it seems to be reinforced because you have this magnitude, it would be this amount of those, and so forth. That doesn't mean the original value is correct. Okay, it just means that this is what's in use. And that applies to other things that have been calibrated as well. You have to have, you're assuming that the original interpretation and value chosen is correct. That doesn't verify that it is correct. It's just what we use. That's very important to understand.